Hello everyone! In this video we will continue to examine topic 7.1 discrete energy and radioactivity, and in particular we will continue to discuss half-life, radioactive decay, and background radiation. Alright, so in the previous video we discussed the radioactive decay curve, noting that all radioactive decay follows exponential decay, and can be captured by the equation n of t equals n naught e to the negative lambda t. We also discussed the concept of the half-life, or the time it takes for half the sample of nuclides to decay, and how it is related to the decay constant lambda, or the probability that any particular particle will undergo decay in the next second. So now what we're going to do is discuss this concept of activity, okay, where activity is a formal physical term defined as the rate of decay with respect to time. So how fast are the nuclides decaying? Another way of writing that is that A simply is dn dt. Okay, so if you differentiate n of t, you get the activity. Another way of thinking about it is that activity is simply the number of decays per second. All right? The unit of activity is formally known as the becquerel, written as capital BQ, and the number of decays per second, though it's important to recognize like number of decays is actually unitless. So another way of describing a becquerel is really saying hertz or per seconds. So number of decays per second is how I would recommend you translate becquerel in your head. If there's an activity of 20 becquerel, I would describe that in your head or translate it in your head as an activity of 10 decays per second. That's what it means. So given that, if we start with exponential decay, there's actually a very straightforward process for calculating the activity, and that is, because the activity is defined as dn dt, simply taking a derivative. So if you take a derivative of n of t equals n naught e to the negative lambda t, this is an example of exponential decay, and at this point in your calculus education, I believe you have covered this kind of derivative, and the big secret with exponential decay is that if n of t is a particular function proportional to e to the negative lambda t, then so will the activity. Okay, so the activity is also going to follow exponential decay because dn dt, you simply drop your constant from that original function, and as a result, that negative lambda n naught is simply known as the activity. You could graph it sort of upside down if you wanted to capture that minus sign, but usually what we do is simply define a naught to be negative lambda times n naught, and so the activity will also follow exponential decay. What this means is that you can measure the half-life from either the original exponential decay function for the number of nuclides, or from the activity itself. And this is particularly useful because for most incidences of the detection of radioactive decay, if we're talking about half-lives on normal human timescales, and we'll get to the ones that don't act this way in a moment, it is much easier to detect the activity than it is to detect the number of nuclides themselves. To detect the activity, all you need to do is to detect the decay product. So for alpha or beta or gamma decay, you can detect the ejected particle or radiation using what is known as a Geiger-Müller tube, more commonly known in colloquial science as the Geiger counter. This is that device that you'll see in movies and television where, you're getting close to something scarily radioactive, and the main character is holding this scientific device, and you can hear it go click, 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 so on and so forth. That's the Geiger counter, and what it's detecting is every radiated particle, and what it is measuring is the present activity. But the fundamental idea is that if you measure the half-life of the activity, you also have measured the half-life of the number of nuclides. And that's super useful. Now, there are cases of radioactive decay used in science, particularly looking at the decay of carbon isotopes and other such things, in which we actually, because of the timescales, we actually do process the number of nuclei that are left. So we look at the ratio pre-decay of, for example, carbon-13 or carbon-14 to carbon-12 in order to figure out the time it has been since that sample was created. This is known as carbon dating and is particularly useful. So in practice, though, in general, if you're talking about sort of human lifetime timescales, seconds, minutes, hours for radioactivity, then the measurements of the activity itself are easier to make than the measurements of the number of nuclides. So one thing to note, though, is that if you're measuring the activity that you measure does not actually drop to zero in the way you expect sort of exponential decay to do. At a particular point, almost no matter what, you will see that it sort of flattens out at a certain level above zero. Okay? Now, why is this? It's because everywhere you have background radiation. So there are a number of sources of radioactivity, radioactive decay, and radiation that will affect your measurements with a Geiger-Müller tube or Geiger counter. This is known as background radiation, and significant sources include cosmic rays that are high-energy particles and photons released from cosmic sources, so faraway galaxies, the sun. There are lots of different sources of high-energy cosmic rays. There are also radioactive isotopes in the Earth, the atmosphere, and significant leftover radioactivity from the nuclear testing that was done in the 1960s. So lots of different sources like that. Radioactive isotopes in the Earth, in fact, count for about 50% of the heat to be found in the center of the Earth. So it's actually one of the important sources, for example, of geothermal energy, where half of that heat is left over from the formation of the Earth, but another 50% is actually actively being generated by radioactive material in the core. This leftover radioactivity from nuclear testing is also very important and has significant effects. For example, all modern steel that is smelted and made in the modern era, is of lower quality because of that leftover radioactivity. And actually, to get high quality OG steel, what we do is we dig up usually sunken ships from sort of World War II era and take their steel. It's actually a significant problem to overcome. Now, in this worked example here, and in this source of background radiation, you can see sort of the rough breakdown of that background radiation. And there are a couple of nice problems that show you how or what you might be expected to do for a problem concerning radioactive decay. And I would encourage you to work your way through it.